My name is Ali Hassania, and I am currently an aerospace engineering major at the University of Maryland. Today, I will be conducting an engineering breakdown of the Bollman Truss Railroad Bridge. The bridge we are investigating today was designed by Wendell Bollman in 1852. Bollman was a self-taught Baltimore engineer and a Maryland native. Built in 1869, the bridge served to support the railroad traffic in and out of the Savage Cotton Mill in Savage, Maryland. When the mill shuttered its doors in 1947, the bridge fell out of service. It is now open to public use and those walking on the Savage Mill Trail. What is so interesting about the Bollman Bridge is that it is the last remaining example of a feat of American engineering. No other bridges remain in the world with the same Bollman design. It is such an American icon that, in 1966, under a new program for the American Society of Civil Engineers, it was named the first ever historic civil engineering landmark. In addition, after being on the National Register of Historic Places for 28 years, it was given the title of National Historic Landmark. This status is only granted to about 3% of the over 90,000 places on the National Register, meaning we have an enigma of industrialization less than 20 miles from campus. In analyzing the bridge, we can apply units from ENES 102. We can use Unit 2 and 5 to draw the free body diagram of the Bollman Bridge and identify its key components. Taking the free body diagram, we can then apply equations of equilibrium and find various forces throughout the structure. We can also use equations from Units 7 and 8 to find the diameter of the steel wire cables within the structure and the critical load of the wrought iron cords. It is important to note the breakdown that occurred before analysis can begin. The bridge itself is in two mirrored identical halves, so we will only focus on the left portion. Additionally, the structure is formed from a combination of support systems. We will be focusing on the Bollman system that includes the diagonal tensional cable members. What is not included are the 6 steel frames that span the length of the bridge. I'll begin by identifying where we will calculate our values from. The tension is found in the 10 cables over multiple lengths spanning the bridge. On official documents, these are labeled B1 through B10, left to right. The cable diameter value will be found from analyzing cable B1 on the very left side of the bridge. We will then find 2 critical loads from cord BC1. There are 6 wrought iron cords on the bottom of the bridge, officially referred to as BC1 through BC6, left to right. We will first find tension in the bridge's 10 cables. To do so, we will use the sum of forces in the x and y directions when analyzing each point, labeled I through M on the diagram. Because the bridge is assumed to be in equilibrium, we can say both the summations equal 0. In using the summation of forces in the x direction, we need to make sure that each force is measured relative to the x-axis. So we can say that the force in the x direction is equal to the tension of said cable times cosine of inverse tan of the opposite length over adjacent length. The same can be done for the y forces, but with sine. Our findings produce the following. The greatest tension was in cable KG with 7.54 kips, while the lowest was in cable IA with 4.41 kips. A kip, for reference, is 1,000 pounds of force. We can then find the diameter of a cable on the Bollman Bridge. For this purpose, we will focus on cable B1. To find said diameter, we can use the safety factor equation and the design stress equation. From the safety factor value of 3, calculate normal force is 6.49 kips, and the given yield stress, we can first calculate the design stress. That value can then be plugged into the safety factor equation to produce a diameter. The calculation found that the diameter of cable B1 was just under an inch. The last calculation is in finding the critical load of a member on the Bollman Bridge. For this purpose, we will focus on cord BC1. To find said value, we can use the equation of Euler's critical load for pin ends. When looking into the history of the Bollman Bridge, it has undergone many retrofittings throughout its time standing. From this, 2 moments of inertia were supplied, the one for the original B1 member and the one for the retrofitted B1 member. The calculation produced 2 results. The critical load of the original member was equal to 18.3 kips, while the critical load of the retrofitted member was equal to 21.58 kips. This value represents under what force the member will fail and ultimately buckle. Because I'm an isolated college student finishing this project right before finals week with access to limited time, supplies, and mental endurance, I unfortunately cannot construct a replica of the Bollman Bridge. I can, however, supply some helpful context of the loads. For this exercise, imagine cable KG was a wire holding up a ceiling light. If that wire were as strong as cable KG, it would be supporting the force exerted by not one average human, but 55 of them. It could also be supporting 2 2009 Ford Tauruses or even a whole hippopotamus. That's a lot of mammal. For a second reference, imagine the wrought iron member we analyzed for buckling as a bar stool. In order to crush or buckle the bar stool, you would need to exhibit a force of not 1, but 157 average humans. If that proves too difficult, you can always put a Taurus on the stool. Make that 6 Tauruses. And if that's still too daunting of a challenge, you can airlift in a hippo, and then airlift in 1 2/3 more hippos. PETA may not be happy, but it's okay. It's for science. That is the end of the Bollman Bridge engineering breakdown. I thank you for watching and listening today. In the spirit of the holidays, I found it only fitting to showcase a photo of the Bollman Bridge this time of the year. Happy holidays.